Okay, I think we'll get started. So today we're talking about rigid rotation, or rotation of rigid bodies. And so what we can think of here is something that doesn't distort upon rotation. So something like a rock, this pen, if it rotates, it's not going to distort its shape. Now we could compare that to maybe a system of masses and springs, or a water balloon or something. We throw that, that's going to distort its shape. So that wouldn't be considered a rigid body. Now, molecules are not rigid bodies, but in many cases, we can treat them as rigid bodies, or so-called rigid rotors. And that's important in understanding the rotational dynamics of molecules, rotational spectroscopy. And so even though, yes, a molecule isn't strictly a rigid rotor because its bonds can stretch, it often can be treated as a rigid rotor. So it's important for us to learn about rigid rotation. And so we'll do that here today. Now, let's imagine an object that is rotating like this on a circular path. That circular path will have a certain radius r, and that radius will be fixed. And compared to, say, the x-axis here, that will be at a position or at an angle theta from as measured from the x-axis. Now, if we think about this, to describe the circle in the 2D plane, one way we could do it is by specifying the x and y position of this particle at any given instant. And so at first glance, it appears like this is a two-dimensional problem. But in fact, because of the constraint here, this idea that the radius has to be constant, all that one needs to specify to determine where this is in its circular path is the single dimension theta. So this is actually a one-dimensional problem. And so it's compared more directly with just one-dimensional linear motion than 2D motion in the plane. Now, we can specify this position by the angle, as we said, or the distance along the arc running from the x-axis to the position of the object. And that's something called the arc length. And so the arc length is the radius times the angle. And let's take this angle through 2 pi. Then the arc length would be 2 pi r, which of course is the circumference of the circle. So the arc length is a distance. Now it's a curving distance, but we can imagine just tracking this distance along this arc, so it still is a one-dimensional parameter. All right, well, if we've got motion, of course we want position, we want acceleration, and we want velocity. So let's work through that. Let's take our formula and say, well, what if we make it just a ever so slight change? Call this a d, ds, and then r, of course, doesn't change, but that will require a slight change in angle. And so there's a relationship between a slight change in the arc length and the slight change in the angle. Now let's take this as over a particular infinitesimally small unit of time. So ds dt. Now, if you haven't had calculus yet, then you can think of this as ds, or delta s, delta t, and turn all these d's into deltas. And as long as the change is not too significant, that will be fine. But we will write this as d's and use just a little bit of calculus here. So ds dt is r times d theta dt, and that defines what we call the angular velocity And we define, usually the convention is that if it's going this way, so counterclockwise, that's positive rotation. And if it's going this way, then that's negative rotation. So we do say a velocity instead of a speed, although sometimes we'll say speed, to indicate that there is a magnitude and a direction to this. Now, let's look at the units here. This is angles. This is an angle per second. Well, angle isn't, I mean, it isn't really a unit like a meter. So this would be like radians per second. And so it is a frequency. So we can think of the angular velocity as what's called a circular frequency. And this is related to the so-called linear frequency, just our regular frequency that we've seen before, by a factor of 2 pi. And the 2 pi is related to the fact that this is on a circle, so we'll see 2 pi's coming in everywhere. And so there's, you'll see omegas as frequencies, you'll see f's as frequencies. Sometimes in a lot of books, f is the Greek letter nu, so you might see nu as the linear frequency, and the relationship there is a factor of 2 pi. So this feels like they're different things, angular velocity and circular frequency. In the context of the problem, it might be easier to think of it or conceptualize it as a circular frequency, and in other problems, it might be easier to conceptualize it as an angular velocity. Now, let's look at two objects that are, say, on a stick here. And so we've got this stick, we've got these beads, and we're going around this circle. These will have equivalent angular velocities as this thing moves, but because this is on a longer radius, R2 is greater than R1, the velocity of R2 will be bigger than the velocity of R1, or the speed around the circle. And so what we see here is that the radius leverages these angular quantities. So we see the distance is the angle leveraged by or multiplied by r. The velocity is the angular velocity multiplied by r. And that's a common theme we'll see throughout, and we'll keep adding this connection as we learn more and more things associated with rotational motion. All right, let's quickly pick up acceleration. Well, acceleration is just the change in velocity. So angular acceleration is just the change in angular velocity. And again, if you're not yet doing calculus, then you can write that like that. And again, here we see that the acceleration is leveraged by a factor of r here again. And so to summarize, we have this relationship between the linear motion and the rotational motion. Angle plays the role of position. We've been calling that x, but in this context we'll call that s. Angular velocity plays the role of velocity, and angular acceleration plays the role of acceleration. And they're linked together by these formula. This one, and this one. Okay. All right, well, let's shift gears a little bit. So still talking about the rigid body, but how many coordinates does it take to specify this? Here we saw it was 1 coordinate. Now let's think about 3D space. So if we really did have a rock or a molecule that we could consider as rigid, or this pen, well, we could think about the bulk motion of the whole thing. And this is called the center of mass motion. So this pen will have this center of mass about roughly in the middle of it. And if it's moving through space and rotating, right, so the general motion would just be motion in 3D space and rotating in some way. The motion in 3D space captures the linear x, y, z motion of the center of mass. And that's translation. The whole thing is moving. And so there are the number of dimensions of translational motion as the dimension of the space you're working in. So in our laboratory here, it is 3D space, so we'd have 3 translational degrees of freedom. If we're talking about motion in a plane, then, so like on the sheet of paper, then we would have 2 translationals, x and y, degrees of freedom, as they're called. And finally, if we were in a one-dimensional linear motion problem, and that we could say the physics is, we can understand the physics by just motion in a line, then we would have 1 translational degree of freedom. Now, the rotation itself, we can break the rotation down, any arbitrary rotation, into, and I'm going to use something else here, I'll use this stapler, into rotation about each of the 3 axes. That's one way to break down the motion. So we have this rotation, we have this rotation, and then we have this rotation. So we're rotating about the z-axis, the y-axis, and the x-axis. So that gives us an additional 3 degrees of freedom if we have an object that's not linear. Let's look at a linear object, and let's imagine this is infinitely thin. So pretend it doesn't have any width here. So this would be like 2 point masses connected with a stick. So, or in particular, like an oxygen molecule. So imagine this is an oxygen molecule, oxygen here, and we rotate. Well, we can rotate this way, right, about this axis. We can rotate about this axis. But if I just sit and spin, and I'll rotate now this way, if I just sit and spin this way, that's not a rotation. Nothing is moving about the center of mass. So rotation has to constitute some part of that, or that object is rotating or moving around its center of mass. And so we have special cases here now. If we're nonlinear, we have an additional 3 degrees of freedom. And if we're linear, we have 2 degrees of freedom, if we're in 3-dimensional space. Okay? Now, if we're in 2-dimensional space, stuck on a sheet of paper, then we only have 1 degree of rotational freedom. And so it's a little bit different thinking about the rotations than the translations. All right, that leads us to this idea of parameter space, and in particular, trajectories in parameter space. And so let's just take an example of one-dimensional center of mass motion, and then one-dimensional and one dimension of rotational motion. So let's imagine we have this frictionless wire and this special setup where we've got 2 masses and a little ring here, and this is rigid, and the ring is pointing straight out at us like this, and it's free to rotate around, and then it's free to slide along, so it can rotate out at you and slide back and forth. Let's think about the parameter, the degrees of freedom, and then the parameter space. So this motion, this is the whole system here. This breaks itself down. It's equal to the center of mass motion, center of mass, and then the rotation. So we can think of the 2 motions separately or independently. And therefore, what we can do is we can create a graph with 2, in this case, 2 independent variables. Playing the role of the x-axis will be the position, so we will call that x. And then playing the role of the y-axis isn't a y position, but it's this parameter. It's the parameter describing where in the rotation it is. So imagine we're going to key off the top of the cap here, and we're measuring then from the horizontal. Okay. Well, if we call this distance 1, so we'll just work in any kind of unit that would make that 1, then our x-axis would go from 0 to 1, and our y-axis, or our theta axis here, would go from 0 to 2 pi, because we can complete a full 2 pi rotation. What the object does then, its motion, is captured in what's called a trajectory. Okay. Let's go through a few examples here because this won't be in your general chemistry or general physics book that you're working through. Whatever book you have, it won't be in there. So let's look at this with a couple of specific examples. Let's take one case. Let's imagine, here, let me mark. This as our wall. So let's slide all across here at a constant speed or constant velocity, and while we do that, we will do one full rotation. So as we start here, we will do one full rotation at a constant rate through that motion. Let's try to draw the trajectory. Well, we'll start at 0 angle and position 0. We're moving along here at a constant rate, and our angle is progressing at a constant rate. So we're going to end up at 2 pi and position 1, and it will be a straight line. So that will be the trajectory for that type of motion. Well, let's rotate a little faster, but still constant rate. So as we slide along, let's go 1, 2. Let's plot that in blue here. Constant rate, constant rotation, but we made 2 full rotations. So think about what that trajectory is going to look like. Well, where were we after we made our first rotation? We were halfway across, right? Because the whole way took 2 rotations, everything was moving at a constant rate. So halfway across, so at 1/2, will be at 2 pi. Now where do we go from here? Well, 2 pi in the rotation is identified back with 0. So 2 pi and 0 are the same point. And then we continue one more loop, and we would look like that. Okay? So that's 2 rotations. Let's do some more examples. Let's do this. Let's go here. We're at 90 degrees, and then we'll turn around and go back. So 90 degrees, pi over 2. We ended up halfway. Right? We ended up halfway. And let's say we did that at a constant speed. It looks like that. Right? Now, we might be tempted to do that, but we never ended up over here. Right? We just went straight back the same path. Just like that. Okay, so that would be its trajectory. So those lines it just drew right back on top of itself. Let's do a little differently. Let's go halfway again, but now let's freeze and come straight back. Okay. Well, now we go halfways up. Or not halfway, but pi over 2, I guess. Now we're at pi over 2 as we make our way back. Okay. And so notice these trajectories are not functions necessarily. This does not satisfy the vertical line test to be a function. So these trajectories are not functions. They're curves in this parameter space, but not necessarily functions. Okay, let's do a couple without constant motion. Let's say we have constant rotation, but we're going to start slowly. We're going to be rotating. We're going to be moving slowly and then pick up. So we'll be accelerating as we rotate. So because we're going slowly at first, that means we're going to pick up angle faster than we're moving sideways. We're still going to end up at one rotation, but the last part of that motion, because we're accelerating, we cover a lot of ground in the last few radians of rotation. So that would look something like that. Okay. All right, so again, this is not something that'll be in your book, so it's something you'll have to practice on your own. But just try to think about the motion. This is a good system to think about, but you can concoct some other systems. It's easiest to work with just 2 degrees of freedom because you can write them as just in a 2D graph. But if you get really good at that, then think about additional degrees of freedom. So let's say this was free to move anywhere in the plane and also have that rotation. So then it'd be x, y, and theta. And you'd have a 3-dimensional space for your parameter space. So there's lots of ways you can think more about this and practice these ideas. I think it's just good to get you thinking about these things at a little more sophisticated way, and it gets you away from the math a little bit as well. So you're thinking about these things and developing an intuition. This is related to something called phase space, which we won't talk much about. A little bit, we'll introduce it in this sequence of courses. But later in our curriculum, we'll have that comes up a lot. In particular, we'll have some courses on mechanics, so advanced mechanics, and we'll see understanding these types of spaces are really important. Coordinate space, and parameter space, and phase space.